Another important property to understanding the first derivative test is that minimum and maximum values always occur at critical values. Going back and looking at the previous graph where we figured out, okay, there's a critical value on this function at those particular 5 locations. One second while my tablet is for some reason turned off. But this function had a critical values at -5, -3, -1, 1, 4, and 5. Actually 6 values, I misspoke. But basically, notice that some of the, and I mentioned this last time, is that some of those critical values correspond with minimum or maximum values. So returning to the terminology, an absolute minimum or maximum is a location where it's the smallest value in the entire graph. Like right here, we would call this the absolute minimum value because it does not ever go below this. Whereas this point over here would be called a relative minimum because in the immediate vicinity, it's the smallest thing around. But looking at other places, there's values that are lower. And like this point right here would be called a relative maximum because in the immediate vicinity, it's the largest, but as the graph indicates, it actually will go larger to the left. Whereas certain points, the points which the curve was not differentiable, well, not including this point, but these particular points, it actually would not correspond to relative mins and maxes because it's not larger than every point in the immediate vicinity. So, another kind of applying this is if we can find the critical values in a mathematical function like we did in these couple examples, we can also use those to determine, well, is there a minimum or maximum in this location, whether it be absolute minimum or a relative minimum. So like revisiting this previous question, which asked which critical points of f of x equal to x to the fourth plus 4x cubed minus 2x squared minus 12x are relative maxima and minima. And so like looking at the graph, this is the one where we found the derivative and we solved the zero values by factoring. And we use those to determine the intervals of increasing and decreasing, which, we figured out the critical values occurred at -3, -1, and 1. So, and what this is saying is that sometimes critical values correspond to minimums or maximums. And the general term for a minimum or maximum is called an extremum. So if you see the term extreme value or extremum, that's just another way of saying either minimum or maximum. So like, one sec, this is not doing what I thought it would do. I don't know what's going on, but it will not. Okay. But basically this function, as we determined before, had 3 critical values. At -3, I'll just write C1 and C2 and C3 so I can specify which is which. And looking at the graph, which we also graphed in a previous video, we could see that at -3, when x is -3, notice that we get a local minimum value. So this corresponds to a local minimum. When c was equal to, or when x was equal to -1, we got this critical value, which occurred at -1, which corresponds in this case to a local maximum. And when x was equal to 1, in the third critical value, we got a local minimum once again. And another thing is actually, notice that the absolute minimum on the graph actually occurs at both of these spots. So you could actually call these absolute as well. They're both, technically it's not a unique absolute minimum, but there are 2 minimum values to this function which are at both points. But this question just asks us for relative, and relative is a synonym to local. So yeah, like I typically call them local maximums, but that means the same thing as a relative minimum or maximum. But in these case, I'll just write they're a tie for the absolute minimum value. Usually absolute minimum means it's the only one, but I'll just write that in this particular case because it will not go any lower. So let's go back and look at example number 4, to where we found the critical values by taking the derivatives, setting it equal to 0, and solving. And that's always the thing you want to remember. If you're trying to figure out where it's increasing, where it's decreasing, where the critical values are, where the minimums, where the maximums are, all of them are kind of the same idea. Take the derivative, set it equal to 0. That will help you determine these because there's a connection between where the critical values are, where the curve is increasing and decreasing, and where those mins and maxes are. So again, for G and H, we already know the critical values. G had 1 critical value, which was at -3. Let me just double check from our previous page. Yes. And h had one critical value, which was at +1. So if we want to know, well, is it a minimum or maximum value, or is it neither? We could always go to a graph, or we could use what's called the first derivative test. So let's go ahead and talk about how that test works. So the first derivative test says for any continuous function that has exactly one critical value in an interval. So what the importance of this is to be differentiable, it has to be continuous. But this doesn't actually, it just means that it has to be a curve. It doesn't have any weirdness, breaks, gaps, things, asymptotes, things like that. And specifically, we have to have one critical value in the interval that we're looking at. Then the first thing says that f has a relative minimum at c if the derivative is negative or less than 0 on AC and the derivative is positive on CB. So basically what this is saying is another way of reading this is we have an interval AB where we're looking at our curve, which I'm kind of imagining is here. C is somewhere in the middle, which is the location of our critical value, again, why we call it C. So kind of imagining these intervals, this is sort of what I'm thinking in my head. We have A and B, and I have a critical value somewhere in here. And what we're kind of looking at is, well, to the left, if it has a relative, if its derivative is 0 on AC over here, or sorry, if the derivative is less than 0, meaning I'll go ahead and just write this as a negative derivative with the negative sign. If it's negative over there, that means that it's decreasing. And then part 2 says and if it's positive on the right half from C to B over here, that means it's increasing. And of course, if we can imagine our curve is changing from increasing to decreasing, that would indicate that there is a minimum value in between those points at the location of the critical value. So another way of reading this is we can check the derivative to see, is the derivative negative on the left and positive on the right? If that's the case, then f is decreasing to the left and increasing to the right. And that implies that it has a relative minimum, because again, exactly that. If it's changing from decreasing to increasing, that means that it's hitting a bottom and there's a bottom value there. And the second part of this is exactly the same logic. It says it has a relative maximum instead if it's positive derivative on the left, meaning that the slope is increasing over here, going upwards, and the derivative is negative on the right interval, meaning going downward, negative derivative over here. Again, if it's changing from positive to negative, that implies there's going to be a maximum at that point. And notice that this is for relative extrema. We don't know whether it will be the absolute or local or a local min or max, but either way, it will determine that there is a point where there's either going to be a relative or absolute min or maximum value. And it says f has neither a relative maximum nor a relative minimum if f prime of x has the same sign. So, like for example, it could be positive on both sides, which just indicates that it does have to hit a critical value, a flat point in between, or a weird point where either the derivative is 0 or undefined, but it won't necessarily correspond to a min or maximum value if it does that. In some contexts, those are called saddle points. But it's usually in a three-dimensional context. But let's go ahead and look at the examples above. Let's try to use the first derivative test. And again, this graph kind of shows that idea that going from negative slope to positive slope indicates minimum, positive to negative indicates maximum. No change indicates neither a min or a max at that position. And like looking at some of the previous examples, sometimes we had minimums where the slope changed from negative to positive. Sometimes always we had a maximum where it changed from positive to negative slope, and there was not a maximum when it changed from negative to constant or did not change in either case. So if you're wondering, okay, how do I use the first derivative test? But basically what you want to do is, here's your C, pick A and B, because this is the only critical value. You can actually pick whatever you want to be A and B, but what I would recommend doing is just say pick, like, I don't know, negative 5 and 0, whatever numbers you want to the left and to the right. Even more commonly, what we could do is pick numbers directly to the left. So here's my critical value, -3, go 1 to the right, 1 to the left. And here's the interval that we're going to test our derivative on. And what we want to look at is, what is the derivative? Is it positive or negative at those 2 points? Because we already know that the derivative is going to be 0 at 3. It's actually more common for us to label the bottom with the values of the location on the number line. And actually, to be honest, if I was doing this myself, I would use 0 because that's just a much easier number to plug in. Let's just say 0 on the right and -4. But again, basically, you can pick whatever numbers you want, as long as, again, you're making sure that there's only one critical value that you're focusing on and you're not encompassing more than one, because this will not necessarily yield the correct results in those particular cases. So I'll just recap. Okay, we had the critical value at -3 here. And I'll write that using better notation. C happened at -3. And also, we need to know our derivative, because this will help us determine whether it's positive or negative, which was 2x plus 6. We already determined that. But basically, if I want to know, okay, this is going to be either a relative minimax or neither, I can use that first derivative test. And what I want to check is it positive or negative on the left and the right-hand side? So basically, I could plug in -4 into G prime. So G prime of -4 would give me, well, 2 times -4 plus 6. 2 times -4 is -8 plus 6 is going to be -2. So what I know is over here, this is negative on the left-hand side of the critical value. Now on the right-hand side, again, I picked 0, but you could pick anything larger than -3. But at 0, that's just going to be 6, the derivative. So that's positive. So on the right-hand side, it's positive. And again, changing from negative, decreasing to positive, this will be a relative minimum because of the first derivative test. And basically, you could memorize this sort of diagram or put it on a note page or whatever, but it's common sense. It has to do with the slope of the curve. Derivative negative means down. Derivative positive means it's going up. Decreasing to increasing means minimum, and this is all something we could remember just by thinking about that sort of logic and in thinking about an interval of numbers. But it's a visualization tool for helping us remember this. Now, if it did not change, then it's neither. And if it changed from positive to negative, it would be a maximum instead. So let's look at h of x and see if we can determine if there's minimum and maximum. Also, another thing that it says, notice it says minimum and maximum values. A more common way of describing local mins and local maximum points is actually by using the coordinate, using the actual point value of the curve. And actually, we can always determine the coordinate by plugging in it, because basically this would be, again, an x location for where the value is. But, usually we write points as x comma y. So we know that for that minimum, or in this case, it's a relative minimum point, it'd be -3. And if we want to know what's that value of the minimum, that would be the y value, or if I plugged in g of -3. G of -3 would be -3 squared plus 6 times -3 plus 5. That would leave me with 9 minus 18 plus 5. That'd be -9 plus 5 is -4. And basically, I could actually get what is the point on the curve that corresponds to this. And actually, for a quadratic function, this is often what we call the vertex. And you probably remember there's a vertex formula. There's ways of determining the vertex of a parabola. But actually, you can use calculus to find the vertex by taking a derivative, setting equal to 0, and finding that point. And if you go ahead and graph this function with your calculator, you'll see exactly that. This video is getting a little long, so we'll do the next example in the next video.